Hi, this is Mrs. Cribb. We're going to go over the problems on entropy and Gibbs free energy for honors. What I have done right here is I've gone ahead and looked up the values that you need. So first of all, look, we're on example 13-5, which can be found in your textbook on page 340. And also, you'll notice there's a big chart on pages 344 and 345. You'll need to refer to those. That's where you can get all these values that I'm talking about right up here. So what we're going to do is we're going to calculate the delta S. And remember, this is at standard state. So the delta S values you're going to get from your book on these pages. So this is entropy. Entropy is disorder. I like to write it like that. It's disorder. So that you can help you remember that the S stands for entropy. And to calculate entropy, it's just the sum of the entropy of the products minus the sum of the entropy of the reactants. Alright, I went up and looked on this chart and found the entropy of the products. Now you'll have to pay attention to the state this time. It's very important because the entropy of a solid is going to be different than the entropy of a gas or liquid state. So here we looked at ammonium chloride solid and found that it's 94.6 joules per mole per Kelvin. Hydrochloric acid as a gas, hydrogen chloride as a gas, not hydrochloric acid in this case, is 186.9 joules per mole per Kelvin. And ammonia is 192.8 joules per mole Kelvin. So now let's calculate the entropy of this system. The sum of the products minus the sum of the reactants. So the products is this one. So here's the product. That'll be the first part of it. And there's only 1 mole, and you need to do that. You need to write that. It's going to be really, you'll put it in brackets because sometimes you'll have more. And we have 1 mole of NH4Cl, and the S, the entropy is 94.6 joules per mole times Kelvin. And that's the sum because it's only one value this time, minus the sum of the reactants rather. There's 2 reactants. Again, we have 1 mole of ammonia times 192.8 joules per mole Kelvin. And since it's the sum, we have to add together the next reactant, and we have 1 mole of hydrogen chloride times 186.9 joules per mole Kelvin, and then close the brackets. Now you just add these two together and subtract it from this value to get the final value. Okay, and what I did is I stopped it for a moment and fixed this, and notice that oh, there's my pen. I crossed out right here the moles. Moles cancel out on all the way through, so the unit is just joules per mole. Now I added these two together and I got 379.7, and just subtract these values to get the final answer. And the final answer is, where'd my pen go? There it is. Negative 285. I don't know what's happening with my pen here. Sorry about that. Alright, I'll use my cursor for a second. Negative 285.1 joules per Kelvin, not per mole. I wrote that down wrong over here. This is Kelvin. Okay, that's really sloppy looking. I'm sorry about that because I'm writing with my cursor, my mouse, rather than my pen for a moment. Okay, recap. To calculate the delta S, you take the sum of the products minus the sum of the reactants. There's only 1 product, so you don't have to really add anything together. There were 2 reactants. We had to add those together. So now we take those values, product minus reactant, to get the final value of negative 285.1. Now notice that negative 285 means that we're decreasing our entropy. Entropy is disorder, and when we decrease disorder, we're increasing order. So a negative value is right here, it decreases it, it goes against nature. So a negative value goes against the tendency, and it attempts to decrease entropy, and that is not favorable. A negative value is not favorable. Negative delta S, whoa, a negative delta S is not favorable. Favorable conditions are positive delta S. Okay, we're going to go on to the next one. All right, one thing we're going to do is I'm not going to worry about doing these right here. These are just 4 possible combinations. If you want to look at them, they're on page 340. And so just ignore this area for our purposes right now. All right, we're going down to Gibbs free energy. J. Willard Gibbs, he figured out a way of putting entropy together with enthalpy and created a new formula. And it's delta G equals delta H, which is that heat, the enthalpy that we've already talked about, minus the temperature times delta S. And the temperature is in kelvins. That's important. So this delta H we have calculated already. Delta S we just calculated something. We can put them both into one formula and come up with Gibbs free energy. And we're looking for a negative value. A negative delta G indicates a decline in free energy, and it signifies something that may occur naturally or spontaneous. So we're trying to figure out, would the reaction be spontaneous? And is it going to be spontaneous at certain temperatures? Right here. That's going to have a lot to do with it. And then the values of the entropy and the enthalpy change, the heat change. Okay? A negative delta H is a spontaneous reaction. Products minus reactants, we could calculate delta G products minus reactants just like we did enthalpy and entropy, but we are not going to worry about that one at this time. We're just going to use delta G equals delta H minus T delta S. We're going to use this formula that he used. Okay, so we're going to calculate Gibbs free energy for the following reactions. Again, you can find the values that you need by looking at pages 344 and 345. And so I'm going to stop this for a moment and put those in. Okay, I'm back. Here are the values that I got off the chart from page 344 to 345. Remember that, 344 to 345. Look at those charts carefully. You have to just kind of go down. The delta H of formation for Ag2S, and it's a solid. You have to always look at the state. Ag2S solid. Delta H of formation is negative 32.6 kilojoules per mole. Now, the deal is we only have 1 mole right here, so it's just going to end up being, when we put it into the formula for delta H, the delta H is just 1 mole of it, so it's just going to be kilojoules. The entropy, the delta S for solid silver is 42.6 joules per mole times Kelvin. The entropy for sulfur solid is 32.1 joules per mole times Kelvin. And the entropy for Ag2S is 144.0 joules per mole Kelvin. We're going to need all those values. Now we're going to calculate Gibbs free energy. So delta G equals delta H minus T delta S. The temperature has to be in kelvins, and that's already there. All right, the delta H I was just given, so I put that in. Negative 32.6 kilojoules minus the temperature, which is 298 kelvins. And then I have to have the delta S. Well, I don't have that right here, so I have to calculate it and then put it into my formula. So delta S equals, and I do this quickly, the sum of the products minus the sum of the reactants. And I don't go through the standard state and every time I write it. All right, the product, we have 1 mole of Ag2S, and the Ag2S value was 144, so 144.0 joules per mole Kelvin, and that's all the products I have minus the sum of the reactants. 2 reactants right here. So I have 2 moles. Notice that this time I have 2 moles of silver, so I have to write that here, 2 moles, and then I'm going to go back to blue just to so you can connect the dots there. The 2 comes from there, it goes to here. And of silver, it is 42.6 joules per mole times Kelvin plus, because it's a summation, the value for the sulfur, and I only have 1 mole of sulfur. 1 mole times 32.1 joules per mole Kelvin. That's the end of the summation sign. I'm going to cancel out units. Moles cancel. And then I'm going to add these and then subtract it from this value. So I'm going to pause it and put those values in. Alright, I've done the math on these. All I did, multiplied this times 2 and then added that to get 117.3. And then, so it's 144 minus 117.3. When I subtract those, I get 26.7 joules per Kelvin. So that is your delta S. And that goes right here. 26.7 joules per Kelvin. I should have scooted that over a little bit. Alright, now I just need to multiply these. I'm going to show you again the canceling of units. Kelvins cancel. So now we just have kilojoules and joules, and that's an issue. We're going to have to fix that. Alright, so let's go ahead and put those values in. I'm going to go ahead and change my kilojoules. Well, let's just see what this value ends up being. Alright, negative 32.6 kilojoules minus 298 times 26.7. 298 times 26.7 is 7,956.6. All right, 7,956.6. I'll write that down. 7,956.6. Now 3 sig figs, so 7,960. 7,960 joules. Okay, so we have some kilojoules minus some joules. I think this time I'll just go ahead and change the joules to kilojoules. So I'm going to divide by 1,000 because when you go from joules to kilojoules, it's going to be a smaller number because kilojoule is much larger. So I'm going to divide it by 1,000. 1, 2, 3 spots. So it's negative 32.6 kilojoules minus 7.960 kilojoules, and that's going to give me my final value, and my final value is negative 40.56 kilojoules, but we have to do sig figs. It looks like it ends right here because we're subtracting on the tenths place. We have to end right there then. So negative 40.6 kilojoules. That's what delta G is. Now, is that spontaneous or not spontaneous? Well, just look back up. A negative delta G means it's spontaneous. So this is a spontaneous reaction. Okay, let's do the next one. Example 13-7. We're going to calculate Gibbs energy again. I'm going to look on pages 344 to 345 to get the values that I need. I'm writing the formula first. Delta G equals delta H minus T delta S. Alright, and now I'm going to go get all my values and write them over here. Okay, I went and got them for you. The delta H of formation for iron 3 oxide is negative 824.2 kilojoules, and it's 1 mole, so it's I already got rid of the mole because it's only 1 mole of this, so that would cancel out. The entropy for iron 3 oxide, the solid form, is 87.4 joules per mole times Kelvin. The entropy for solid iron is 27.3 joules per mole times Kelvin, and the entropy for oxygen, gas, is 205.2 joules per mole Kelvin. All right, so we can fill in our value here. For H, we just use the value we looked up, negative 824.2 kilojoules. Minus the temperature is 298 kelvins, right there. And then, of course, we have to calculate delta S again. So delta S is the sum of the S of the products minus the sum of the S of the reactants, which is going to equal, for the products, we have 1 mole times, for iron 3 oxide, of 87.4 joules per mole Kelvin, plus, I got to subtract it. Let me erase that real quick. Minus the sum. So we minus the, let's see here, we have 2 moles of iron. I'll put that a different color. 2 moles of iron times its value, 27.3 joules per mole Kelvin, plus, that's where it comes in. We notice this time we also have this. Don't worry about this 3/2. It's only there because they wanted this to be 1 mole right here for this particular purpose. Normally you would use a balanced equation with no fractions in it. So 3/2 mole times, for oxygen it is 205.2 joules per mole Kelvin. I'm running out of space for my units. Joules per mole Kelvin. Okay, now we go through and cancel units out. Moles all cancel. We're going to multiply these guys so that 2 times this and 3/2 times this, and then add it together to get one value, and then we'll subtract it from 87. So I'm going to pause it and do that real quick. Alright, I went ahead and did a little bit of math. Multiplied 2 times 27.3 to get 54.6. Multiplied 3/2 times 205 to get 307.8. Now we add these two values together and we get 362.4 joules per Kelvin. Now I need to just do the subtraction. So 87.4 minus 362.4, and I get a negative 275 joules per Kelvin. So that's the delta S. That's the delta S I need to put right here. So delta S is a negative 275 joules per Kelvin. All right, so now we just need to do the math again. Multiply these two, and you'll notice that the units again cancel, kelvins and kelvins. So it's going to be a negative 824.2 kilojoules minus 298 times a negative 275. And that gives me this number here, negative 81,950 joules. And so to subtract a negative, you're adding a positive. And so when I add these two values together, I get now notice this is joules and this is kilojoules. I've got to quickly do that changeover. So divide by 1,000, 1, 2, 3. So really we're going to change it to negative 81.95 kilojoules and add that to 824.2 kilojoules, and that will give you an answer of negative 742.25 kilojoules. So it's kilojoules, and I turn this into kilojoules. Now this ends in the the tenths place rather, so I've got to round, and I'm just going to not worry about the honors rounding to even, and negative 742.3 kilojoules. That's delta G. It's negative. It is still spontaneous. All right, next equation. All right, I stopped it and put in some values for you. I looked it up again on page 344 and 345, and I found that the formation, the delta H of formation that's needed in the formula, delta G, delta A is equal to delta H minus T delta S. The delta H of formation is 227.4 kilojoules, so that's what I put right here, minus the temperature of 298 kelvins. Now I have to calculate your delta S. Delta S is the sum of the products minus the sum of the reactants. The product delta S is C2H2, so I looked up C2H2. Oh, I didn't. I need to find it real quick. All right, there it is now. I have it. It is at 200.9, and it's 1 mole. So 1 mole times 200.9 joules per mole Kelvin. And then the summation for the reactant side, we have 2 moles this time of copper. So 2 moles times the value for copper, carbon, forgive me, 5.7 joules per mole Kelvin, plus, because it's a summation, we only have 1 mole of hydrogen times 130.7 joules per mole Kelvin. All right, go in and cancel out all the units. That will cancel, moles cancel all the way through. Multiply this and add it to this, and we're going to subtract it from 209 joules per Kelvin. So I'm going to do that real quick and put it there. All right, I did the math, and 2 times this is 11.7. Add it to 130.7, I get 142.1. Now I'll just subtract 200 minus 142, and I get 58.8 joules per Kelvin. This is the delta S. So I put that over here, 58.8 joules per Kelvin. Now I'm going to multiply and subtract it out. Now notice again that the kelvins cancel, so I'm going to end up with joules. So 298 times 58.8 is 17522.4 joules. Now I'm going to convert joules into kilojoules so I can do the subtraction easily. So divide by 1,000, 1, 2, 3. So this becomes kilojoules, and there's a decimal there now. So it's 227.4 minus 17.5224. Okay, and that gives me 209.8776. Okay, again, ends in the tens place, so 209.9 kilojoules. Now notice this time, it's positive, so it's not spontaneous. All right? Positive, not spontaneous. We have at least one more to go. Okay, I went ahead and got some values for you, and so we look at it. Here's the formation, delta H formation. It goes right here. There's the same formula. Delta G equals delta H minus T delta S. The temperature is still 298 because it's right there. Delta S we have to calculate. It's the sum of the products minus the sum of the reactants. There's 1 mole of product, so 1 mole, so the moles cancel. And there's the value right here, 219.3. And then the reactants, there are 2 moles of carbon, not copper, and so the moles cancel. And that's a K. And then there's 2 moles also of hydrogen, so the moles cancel. So we're going to multiply both of these together, add them up, and subtract them from 219. So you just got to be careful. I'm going to go ahead and calculate the final value and put it here for you. Just be careful when you're multiplying these. Add those together, and then subtract the reactants from the product. Alright, so if you multiply 2 times 5.7, you get 11.4. Multiply 2 times 130.7, you get 261.4. We add these guys together, we get 272.8 joules per Kelvin, and then we do the subtraction, and we get a negative 53.5 joules per Kelvin. Put that over here, negative 53.5 joules per Kelvin. Now we're going to multiply these guys together, and we're going to subtract it from 52.4, and I'm going to put those values in. Alright, I put the values in. I got rid of the kelvins, multiplied these two values to get a negative 15,943 joules. Again, I'm going to turn it into kilojoules. 1, 2, 3, divide by 1,000. So now it's kilojoules. So 52.4 minus a negative, that means we're going to have to add 15.9. And that final value ends up being 68.3 kilojoules. That's after we go ahead and adjust. So now it's a positive delta G. It is not spontaneous. Alright, I was wrong about having one more. There's another one, and this last one is just comparing what happens at 2 different temperatures. So we're basically going to be dividing this in half. I'm going to divide the table in half and do this really quickly for you. Okay, we need to talk about this last one because this one's a little bit different. Now, what I want you to notice is in the previous examples, every single time we are taking a pure substance and right here, we're taking a pure substance and another pure substance, an element, and creating something. So the delta H of formation for pure substances we already talked about, and that's always a 0. So the delta H of formation for this final thing, since it's always products minus reactants, was always going to be just whatever we got off the chart. Okay, but down here on the bottom, now we're not starting off with pure substances. Our reactants are molecules, not pure substances. So we have to calculate what the change in the heat is this time by using the delta H's of formation, which we've already done this earlier in the chapter. So we're going to have to calculate the delta H of formation for this molecule based on products minus reactants. So that's our first goal. So our first step here is to calculate the delta H of formation. And remember, the delta H is going to be the sum of the H of the products minus the sum of the H of the reactants. So I'm going to go ahead and do that over here, and then right underneath the values, I looked all these values up off the same chart from 344 and 345. So I'm going to use all these values and calculate the delta H of formation. I'm going to write it down right here for you. All right, first let me show you where I got everything from. The product is in H4, so there's the product value, and this is where it is, and there's only 1 mole of it. Then the reactants are in H3, there's only 1 mole of it, and the NH3 value is a negative 45.9. And the second reactant is HCl, there's only 1 mole of it, and the value is negative 92.3. Now I'm going to combine these two values and subtract it to get the final answer. I'm not going to show you all the pieces this time. Okay, here we have the answer. I combine these two values to get a negative 138.2, and that's to the tens place because this ends in the tens place. Then I said take a negative 314 minus a negative 138.2. I get a negative 176.2 kilojoules. That is my delta H. Now I'm going to have to calculate delta S using these values. Okay, I went ahead and inputted these values again for you. Formula still, delta S equals the sum of the S of the products minus the sum of the S of the reactants. The product is NH4, so NH4Cl, there's the entropy of the product, 1 mole of it, moles cancel. And then the reactants are NH3, that's 192.8, moles cancel because there's only 1 mole, and HCl, moles cancel because there's only 1 mole of HCl. So there's the 3 values. Now I'm going to combine these two, subtract them from here to get the change in the entropy. Alright, when I combine these two, I got 379.7. I subtract it from 94.6. I get a negative 285.1 joules per Kelvin. There's your delta S. So now we calculate the delta G's at 2 different temperatures just to compare them. I'm going to set those two up for you. Okay, I put in the final amount for you, calculating the delta G's, and so let's look at them. Here's the first delta G. It ends up being a negative 192 kilojoules. We multiplied the delta H, which we calculated over here, and we subtracted 298 kelvins times the delta S, which we calculated right here, right down here. There's that delta S. We got, by the time I adjusted for joules to kilojoules, so divide by 1,000, 1, 2, 3, and then when you subtract a negative, you're adding a positive. I ended up with a negative 91.2 kilojoules, which is spontaneous. Now we have to do the same calculation at 1,000 kelvins. So the same exact delta H as before, the same exact delta S as before. The only thing that changed is the kelvins. The kelvins cancel again. This time I got a negative, what is that? A negative 285,000. You adjust it to turn it into kilojoules, divide by 1,000. All right, so it's kilojoules now. So it's a negative 176.2 minus a negative, which means you add a positive. We end up with 108.9 kilojoules because we're adjusting to that 1 decimal place. So now it's not spontaneous. So this one is spontaneous. This one is not spontaneous. And the only thing that was changed was the temperature that you ran the experiment at. So that will help determine whether something happens or doesn't happen. This one was a little bit more laborious, but I know that you can handle it. Hopefully this will help you all, and I'll see you soon.